up to now in this course, we have become familiar with the fabrication technologies that we use to make these microsystems, including microelectronic devices. And from this point onwards, we're going to focus on the devices. How do we make devices? How do we analyze devices? We'll learn about the limitations that are imposed onto our device design aspects because of the fabrication, and now with the understanding of how we make these devices, you will appreciate those challenges. We'll see that in actually most situations, we are dealing with simpler problems than the most general situations that you have at macro scales. So for example, we'll see that the cross sections of the beams that we analyze in this course or in the MEMS field is mostly rectangular in nearly all situations. And we don't really have to deal with those arbitrary waveforms that we dealt with before or at micro scales before. Or the loading is, in most cases, either a point load or a distributed load that is applied uniformly to a structure. So then again, we are dealing with a relatively simpler set of problems. Now, the first set of issues that we talk about is, what are the material responses when we look at the mechanical response of these devices. Then we look at the static and dynamic response of MEMS devices. And then we move into the energy transfer methods. The MEMS devices are mostly used as sensors. They have to take some information in the environment, which causes some response from your MEMS device. And then at the end of the story, in most situations, you also need to read that data into electrical domains. So there's a lot of energy transfer between different physical domains. So we learn about those next, and then we go to interfacing and signal processing. So there is a sequence of issues that we're dealing with. How to fabricate them, how to design them, by them I mean microsystems. So how to fabricate microsystems, how to design and analyze microsystems, and then finally how to interface and process signals from them. So the first thing we are going to talk about is the material properties when we look at them as mechanical systems. So the stress and strain, these are definitions that you've seen in your earlier courses. We are going to basically review them relatively quickly and focus on the aspects of those, let's say, knowledge that you have from statics course or dynamics course. We're going to focus on those aspects that are more relevant to our case, to the analysis of MEMS devices. But just general definitions as a reminder. Stress is the internal response of a material to external forces, right? So it is how a material responds to external forces. The unit of stress is pascals. It's the amount of force per unit area. You have two different types of stresses. Normal stresses are the ones that are produced in response to normal forces to the structure. So if I press a piece of material from the two ends, let's say this box, if I press the two sides of this box, it will develop internal stresses in response to those forces that I'm applying to it. It could be tensile or compressive. Compressive is when I push onto this device. Tensile is when I stretch it. Our convention in this course is that we show tensile stress with a positive sign and compressive stress with a negative sign. Shear stress is, on the other hand, where I apply a force parallel to a surface instead of to it, normal to it, I apply the force parallel to a surface. It also causes the formation of the material, and the material response to that shear force is a shear stress. In this case, when I apply a normal stress, I expect the dimensions to change. When I apply a shear stress or shear force to this structure, I apply the angles to change, right? And the material to deform, to change shape in two different ways when we have shear or normal stresses. With these stresses, and I have in 3 dimensions, I have 3 surfaces to apply normal stress and 3 surfaces to apply shear stresses, I will get a matrix like that for all of the stresses that I may have. So sigma 1, 1 is basically when I apply a normal stress to, let's just say sigma xx. If this is x, y, and z, I'm applying normal stress along the x-axis, and I'm looking at the response of the material in that same direction. In that matrix convention, you can see it as sigma 1, 1 or sigma x. I don't really have to specify the other axis. It's the same axis. So same thing for sigma y, y and sigma z, z. But for shear stresses, I need to specify, what is the plane that I'm applying the stress in, and what is the plane that what is the deformation that I'm looking at. So for example, tau xy in that matrix that you see on the slide, it means that the stress is acting in the y direction, but normal to the vector in the x direction. Okay? So by basically, so on tau xy, you can find it on this graph as, let me bring up my pointer. Tau xy is shown here. This is the component of stress. So it is acting in the y direction, or a phase that is normal to the x direction. Okay, so tau xy. And sigma x or sigma xx, the normal stress is here, right? So this is my x-axis, normal stress, the force and the deformations are along the same axis. Because we are talking about the statics, because this structure is not moving, is not rotating, you can show that tau xy and tau yx, for example, should be equal, right? So in a static case, you will see that tau xy and tau yx, which we should have had here, are equal, and I use the same symbol for them. So altogether, I will have 6 independent stress components: sigma 1, 2, 3, or x, y, z, and tau xy, tau xz, and tau yz. Now, the idea here is that we want to see how a material responds to external forces in terms of the internal normal and shear stresses that it develops. The next point here is to figure out strains. Now, instead of looking at the material response in terms of forces and stresses, we want to see how it responds in terms of deformations. And a strain is a measure of how much change in length you have per unit length. It's a normalized amount of deformations. So if you have a structure like this, so let's say u of x and u of x plus delta x, these are the initial, these are the strain points, these are the deformations of the structure. We want to figure out, we define strain this way. So it is basically the change in deformations over that length. For normal strains, it's the change in the linear scales. For shear strains, a similar definition, but you're not looking at the deformation along one line normalized to another. That gives you an angle, because these deformations are usually very small. So instead of using a it's actually the tangent of the angle, but because the deformations are very small, it's the same as the angle itself when you specify it in radians. So for shear strains, we will have angles, right? So, and then we have deformations in 2D, and therefore you get a definition as shown here. Similar to stresses, we will have 6 independent shear strain, normal and shear strain components put together that we can show in a matrix like this. So you have the normal strains diagonally here, and the shear strains are put in the other corners of elements of the matrix. And then again, because of the symmetry, your shear strains x, y, and yx are going to be the same, and xz and zx are going to be the same, because not because of the symmetry, because of the static issue, because things are not moving, everything is in equilibrium. Now, it turns out that the stress and strain are related. We can probably intuitively have a feeling for that, but the deformations of the material and the amount of forces that you apply to it, or the internal stresses that it develops, they are related to each other. For a typical material, as you apply a tensile strain to it, so sigma is the tensile strain, normal strain that you're applying to the material, and Epsilon is sigma is tensile stress, and epsilon is the tensile strain. They are related. Initially for small stresses, for small external forces. Remember, stresses are the responses of your material to external forces. For small stresses, you get small strains, and they are relatively linearly proportional to each other, right? So you get this straight line. So for small strains and stresses, everything is linear. At some point, we will have a deviation from that linear response. The material is undergoing some plasticity, plastic deformations. During the first part, when the strain and stress are linearly proportional to each other, everything is reversible. You remove the stress, the material, or the external force, the material goes back to its original dimension, deformation goes away. But after the yield stress point, after this the proportional limit point A, you can cause plastic deformation. So this, if you put too much strain on this material, it doesn't go back to the original shape. Once you remove the stress, you will have some permanent deformation of the material. If you keep increasing the strain or stress, you will go into a hardening phase, and then eventually the material fails. Now, this is for your typical material, right? Very general situation. And just notice that strain axis is not drawn to scale. You usually don't really get that much of, let's say, range of changes after you go past the yield stress. Things usually happen very quickly beyond that point. But you can see that, you can play with the material response by changing the material composition. So in case of steel, for example, if you go from pure iron, you get a response like that. The linear range is fairly narrow and small, and then you have this plastic deformation range for the strains that is fairly wide, and then eventually it fails. As you add more and more carbon to your steel, up to here where you have high carbon steel, then two things happen. First of all, the range of linear relationship between strain and stress, it increases a bit more. So the material behaves more linearly over a wider range of strains and stresses. And the second thing that happens is that you really don't see a plastic deformation here anymore, right? So for high carbon steel, we call it a brittle material. If you put too much stress on the material, it just breaks. It doesn't go through that plastic deformation anymore. And the reason that I'm showing you here is that those kinds of materials are called brittle materials. They have a linear stress-strain relationship all the way to their yield point. And then after that, they just break, they just fail. They don't undergo all those plastic deformations. And examples of such materials are silicon and ceramics and a lot of, let's say, stone and glass and other kinds of materials that are around you. You really don't see that much of a plastic deformation in these materials. They just show a fairly linear relationship between strain and stress, and then they fail. Silicon is one such material, so it is important from that point of view. So for strain-stress relationship for silicon, you mostly see this linear region and then failure if you put too much stress on the material. Now, if your material has an isotropic response, mechanical response in this case, if there's no internal structure or order, then the stress-strain relationship, you do not expect it to be direction dependent. If the material is the same when you look at any direction, you expect the mechanical response to be independent of the direction. And again, based on our, let's say, large-scale experience, based on our experience from day-to-day life, what you can expect is that if you apply a certain amount of force onto this structure to produce a normal stress because of that force, you expect the deformation to be proportional to that. Especially for a brittle material in its linear range. And we show that dependence through this coefficient here, E, which is called the Young's modulus of elasticity. So E is a constant, it's a property of the material that relates the stress and strain when the device is in its linear range of motion. This is Hooke's law, right? Basically, it says the forces and displacements or deformations are proportional to each other. The unit for E is pascals. Remember, strain is normalized displacement, so it is unitless, and stress is newtons per unit area, so the unit for Young's modulus is pascals. But as you can even see in this figure, the dashed area is, or the dashed line represents the original material, original shape. Before we apply stress, you apply the tensile stress. It becomes longer, the material stretches, but at the same time, its width decreases, right? So what is happening here is that you have a strain in y direction. Remember, strain is deformation, right? You have a strain in y direction when you apply a stress in x direction, or you apply a force in x direction. So the strain in x and y are going to be proportional to each other. You know, the farther you move this, let's say the more you stretch this material, you expect the other dimension to shrink more and more. How much? Well, that dependence between the strain in x and y directions is specified through this coefficient here, nu, Poisson's ratio. And what we have here is that, you know, the strain in the y direction is linearly proportional to the strain in x direction. So if I make it longer here, I will have a linear amount or proportional amount of reduction in that width. But because they move in opposite directions, so when I stretch it in this direction in x, it shrinks in y, or if I press it and compress it in x direction, it expands in y, I have a negative sign for that relationship. So altogether, I have these two coefficients to specify the behavior of an isotropic material in one dimension. The strain and stress are linearly related through E, and the strain in y direction or z direction is proportional to the strain in x direction through this coefficient nu. The Young's modulus typically is on the order of gigapascals for your, let's say, polymers, but it is as high as hundreds of gigapascals for solids like steel or silicon. For silicon, it varies from about 130 gigapascals to about 180 gigapascals, depending on the direction. The Poisson's ratio, again, is going to, it has a fairly limited range. It's typically around 0.2, 0.3 for most materials. But if you look at something like a rubber, the number is larger, right? So for rubbers, if you stretch them in one direction, you see a very noticeable change in the other direction. And the Poisson's ratio is about 0.5. Similar to normal stresses and strains that we relate them through, let's say, the Young's modulus, you can relate the shear stresses and shear strains to each other as well. And this is done through the shear modulus. You can show that the shear stress tau is proportional to shear strain gamma through this shear modulus G. Now, the good news here is that G is not an independent parameter. If you know E and nu for a material, you can go and calculate G from that relationship. So it says basically an isotropic material is the behavior, the mechanical response of an isotropic material is fully defined using only two parameters, E and nu. Both of them can be relatively easily measured. You have done that in your statics courses before. Now, for the remainder of this discussion that we have actually for the rest of the course, I'm going to focus on normal strains and stresses. This is the common situation in MEMS. We normally do not have to worry too much about shear forces. I'm not saying never. There are some situations like, for example, friction, where the entire interaction is a shear force onto the surface, and you have to worry about that. But those are advanced topics that we are not covering in this course. So in this course, for example, in most of the situations, we are concerned about, let's say, the response of a beam to a normal force that you apply to the end of it, or a distributed force that you apply along it. All of them are normal to the displacement direction that we're interested in. Now, so if I want to go and look at the stress-strain relationship in a more general way, I want to have a, let's say, matrix that describes the relationship between all my stress components and strain components with each other, normal and shear included. I can build this matrix. The compliance matrix, which is whose symbol is S, is given by this. So I know that my linear strain is proportional to my, well, normal strain is proportional to normal stress through this E. I know that sigma x is E epsilon x, or I can write epsilon x is E to the minus 1 times sigma x. I also know that there is a dependence on the other stress components. If I have stresses in y and z components directions, they are going to show up in my x direction through the Poisson's ratio. So this is going to take care of it here, right? So these two terms here, if I have a sigma y, it's going to affect my epsilon x through the Poisson's ratio for that direction. Same thing for sigma z. And if my material is isotropic and nothing else is happening, I do not expect to see a dependence on shear strains. So the shear stresses, I expect all those shear stresses to not affect my normal strain. This is the relationship that you can write like that at the end of the story. So this is something that should be intuitive by now, that the normal strain, if you apply a normal stress to the structure, sigma x, sigma y, sigma z, you can expect the strain in x direction to be given by this expression. So this was for x. I expect the same thing to apply to y and z directions as well. So for y and z, I will have similar expressions. The only thing is that in that case, the strain in y direction is proportional to the stress in y direction directly through the Young's modulus, and to sigma x and sigma y through the Poisson's ratio. And same thing for epsilon z. And then I don't see a dependence on shear forces or strain stresses. So all those components become 0. And then same thing for shear strains. I do not expect shear strains to depend on normal stresses. So all these components are 0 here. And for example, the gamma yz, I only be expected to be proportional to tau yz. So there's only one coefficient g to the minus 1 here. The other components here are also 0. So at the end of the story, going back to what we said before, we only have two independent parameters to specify the material response for an anisotropic material. The stiffness matrix, which relates the let's say stresses, let's say on the left side, to strains on the right side, is going to be the inverse of the compliance matrix. But again, it will have most of the components set to 0 because of the independence of these variables from each other. Now, a frequent situation, so now to see how we can use this information. A frequent situation that happens in MEMS is that as you deposit a film on a substrate or as you grow it, usually you have stresses develop inside the material. So for example, if you're sputtering a film on a substrate, the very top of the film will have a, or as you, let's just assume we have a uniform stress here. You deposit this film, let's say at 200-300 degrees Celsius. The temperature rises during the process as you're depositing it. And then you cool this down to room temperature. The metal that you deposited on this wafer has a different thermal expansion coefficient than your silicon wafer. And therefore, once you cool these structures to room temperature, you develop an internal stress. So for a lot of these thin films that we have in MEMS, you have an internal stress inside the film in x and y directions if you assume z is normal to the substrate. So just because of that thermal mismatch between the thermal expansion coefficients, when you cool it down to room temperature and want to use it, you already have a stress inside the material. However, the stress in z direction is 0, at least at the beginning. So with that situation, what you can see is that you can go and show that, okay, so let me look at the strain in x direction. And because sigma z is 0, you can show that the strain in x direction or y direction is given by this expression. Epsilon z, because sigma z is 0, is very small, but for epsilon x and epsilon y, the initial strain, you can show that it is proportional to this amount of sigma. Sigma x and y are the same. We are assuming that the film is amorphous, so basically once you cool it down, the amount of stress you get in all directions is the same, in x and y directions is the same. You can now show that epsilon x and y are proportional to that sigma x and y through this coefficient, E over 1 minus nu. So this is called the biaxial Young's modulus. So it's as if you're dealing with a stiffer material, right? And it is a consideration for MEMS devices. So if you, for example, have a tensile stress in your film and you're designing it, a material from a device from that film that is under tensile stress, you have to keep in mind that if you use the value for bulk of Young's modulus for bulk measurements, you're probably going to underestimate the stiffness of that structure. That structure is going to appear as if it is made of some stiffer material. How much stiffer? Well, considering a nu of about 0.2 to 0.3, the material appears to be 20 to 30% stiffer than bulk material. And that has to be taken into account, especially if you're designing for a given resonant frequency or a given stiffness. You have to take that into account. Or you have to find a way to go and get rid of the stress in your film. And depending on the application, one may be easier than the other. Now, let's look at another situation, another way to take advantage of what we learned so far. So let's assume that we have applied a uniaxial stress to an object. So we just have sigma x equal to some value, and then the values of sigma y and sigma z are 0. And we want to figure out how much the volume of the material changes, that piece of material changes. So once again, you can go back to the formula that or the matrix format that we had before, and just plug in the values for sigma x, sigma y, and sigma z. And what you will figure out is that epsilon x, epsilon y, and epsilon z are this much. Now, this is a normalized amount of deformation. If you have dimensions of the device, let's say delta x, delta y, or initial dimensions, so a, b, and c. Now, instead of a, you have a times 1 plus epsilon x. And instead of b, you have b times 1 plus epsilon y, and so on and so forth. But epsilon y and epsilon z in this case are negative. Now, if you go and plug that into that equation, for a volume ABC at the beginning, now you have a new volume, and you can show that this change in volume is almost, if you ignore higher order terms, given by this expression here. And again, the conclusion here, or the interesting point here, is that if you have a material like rubber, where the Poisson's ratio is about 0.5, you can have a change in volume that is nearly 0. But in almost all other cases, in vast majority of the situations, you get some change in volume. So once you apply a strain to a structure, you will get some change in volume. So it's not that the material redistributes itself and you get the same volume afterwards. You actually have a change in the volume of the material. And for exercise, you can just go at home and see what happens if you apply the same stress in all directions. So for example, if this is a piece of material and I have hydrostatic pressure, meaning that, let's say, I just put it inside a liquid so that you have the same pressure applied from all directions to this structure, what happens to the volume of that structure? And you will actually, you can show that in this case, the change in volume is proportional to 1 minus 2 nu cubed. Now, so what we said so far was for isotropic materials, but the material that is the most important to us is silicon. And we already have discussed, how to make crystalline silicon and all that, and wafers are made of crystalline silicon. We have different orientations and all that. But One point that should be obvious by this point, by this stage, is that if you look at a different direction in your crystal, you will see a different arrangement of atoms. Each direction has its own specific arrangement of atoms. We already have seen how that affects, for example, wet etching, where you get anisotropy in your etching. But mechanically, we should see a difference in performance, right? So depending on how you pack these atoms in one direction versus another, you expect to see a different, let's say, stress-strain relationship for different directions. And this is true for anisotropic materials in all cases. Now, in the most general case that you can imagine, each, let's say, stress component will be proportional to all of your 6 normal and shear strain components. And you get this high-order tensor, 4th-order tensor to describe the relationship between them. However, because of the symmetry between the strain and stress tensors, instead of having a 4th-order tensor, you get actually a 2nd-order tensor, which is a matrix, right? And in this case, you can show that you can relate all the stress components that we have, normal and shear combined, to all the strain components that we have, again, normal and shear combined, through this matrix that has 36 unknowns. Now, we are lucky that, because of the specific crystal types that we have in nature, we don't have any random type that you can think about. There's just only, I think, 21 of them in nature. You get additional simplifications. So let's just focus in case of materials with cubic symmetry, where you have FCC is one of them. So silicon or diamond type crystal shape is one of them. You can actually go and show that the symmetry that you get from the crystal shape reduces the number of coefficients significantly. So in the case of, let's say, diamond-like structure, you only have 3 independent variables: C11, C12, and C44. C44 is for shear, stresses and strains, and C11 and C12 relate the normal stresses to each other. And for silicon, the values are as shown here. Now, here, because we have anisotropy, we have to be specific, what is this matrix referring to, which direction are we talking about. This is for a situation that you have a 1, 0, 0 wafer, and your coordinates, or your origin is aligned with the corner of this unit cell in your crystal. So in that situation, we have these values for C11, C12, and C44. The challenge here is that, well, not all of my beams in my structure are aligned with the 1, 0, 0 direction. Actually, in most situations, they are not aligned for 1, 0, 0 direction. They are aligned with 1, 1, 0 direction on the surface of my wafer for historical reasons. So the question is that, okay, so now that I know this is the way that my material behaves, how do I figure out the relationship between stresses and strains in all directions? What we do here is that we come up with a shortcut. We come up with an effective technique that lets us come up with an effective Young's modulus for any direction in your crystal. And this is extremely helpful. So what this means is that instead of me going and worrying about, what is actually dealing with 3 variables, as we mentioned, for an anisotropic material with cubic symmetry, you have 3 variables. What I want to do is that I want to treat it like an isotropic material with only 2 variables. For isotropic materials, I only had E and nu. For anisotropic materials with cubic symmetry, I have 3 variables, C11, C12, and C44. For MEMS, it's actually one step farther than that. If I can reduce it to some isotropic material, in most cases, I don't really care too much about the deflections in normal direction. So in other words, I don't really care too much about nu, about Poisson's ratio. I'm only interested in deflections along the length of my structure. E is all that I need, in other words. So what I want to find out is an effective technique to estimate E along the direction that is of interest to me. And here is the solution to that problem. So S11, S12, and S44 are the elements of the compliance matrix for silicon. They correspond to basically the inverse of your stiffness matrix that had C11, C12, and C44 in it. You invert that matrix, you get S11, S12, and S44. They are given for different materials. For silicon, this is the numbers that you can use. And what I have now is these L, M, and N, three numbers that specify my direction. So I look at the direction of interest in my crystal, and let's say it is 110. I have the numbers for my crystal, as you can see in this table down here. I go and figure out the angle between the direction of interest and my origin, my X and Y and Z axis. So I call them alpha, beta, and gamma. And L, M, and N in this formula are the cosines of those angles. Right? So once I do that, I can just go and figure out the effective Young's modulus for any direction. So once I figure out what is the relative angles between the direction of interest and my origin, I can go and calculate an effective Young's modulus for all those cases. So here is an example for us. We want to find out the Young's modulus for silicon in 100, 110, and 111 directions. So let's just go through this quickly together. So let me draw the axis here. So okay, so this is X, Y, and Z. And so basically with this structure that is shown here, this is going to be, for example, my 100 direction. Okay. And 110 is going to be 1 unit here, 1 unit here, so it's going to be in this plane. This is 110 direction. And 111 is the one that goes from this origin to out of here. So basically, I'm just going to plot it like this. It's not easy. It's a 3D drawing that we need to have. But what I need to do is I want to calculate the effective Young's modulus in 100, 110, and 111 directions. So let me rewrite the formula that we had here. So it's E is given by this expression here. So S11 minus 2 times okay. And all we need to do is to figure out alpha, beta, and gamma. So L is cosine of alpha, M is cosine of beta, and N is cosine of gamma. Right? So all I need to figure out is the relative angles between the direction of interest and this axis, and then solve the problem. So if I look at this situation here, so let's say for 100, I can see that the angle between the direction of interest and x-axis is 0. Between the direction of interest, again here, and y-axis, that angle is 90 degrees or pi over 2. And gamma is also pi over 2. So what this means is that L is 1, this means that M is 0, and N is 0. Okay? So if I plug that into that equation that I have on top, all of these terms are going to be 0, and therefore I can show that E100, so I'm just going to write it E100, is 1 over S11, and that's, I have the values for S11, S12, and S44. If you look up the value, it's going to be 130.4 gigapascals. So what that means is that for a beam that is along the 100 direction on my silicon surface, the effective Young's modulus is 130 gigapascals, right? If I apply normal stress and strain, normal stress to this structure, the deformations are related with this factor. Okay, so let's look at the 100 situation. In case of 100, let's say, sorry, 110, what happens is that I look at alpha and beta, they are the same. I see that alpha is pi over 4, and therefore cosine alpha, or L, is going to be 1 over square root 2. Beta is the same, so therefore M is going to be square root 1 over square root 2. And gamma, the angle with the z-axis, is 90 degrees, or pi over 2. And therefore N is 0. Combine these and plug that into this equation that we have on top over there. What you can see is that two of the terms will be 0. The last one will be 1 over 2, which cancels with the 1 over 2 at the front. And then if you calculate the number, it's going to be 169 gigapascals. Okay? So for a beam that is along the 110 axis or direction, the Young's modulus is about 170 gigapascals. This actually is your typical orientation for most of your beams. The reason for that is that, in the old days when we had wafers and the wafer had flats, the flat indicated the 110 plane on a 100 wafer or 111 wafer. And then what you did is that when you were doing the mask alignment, you always made sure that this flat is aligning at the bottom. Let's say it's parallel with the edge of the mask. So any line that was parallel to this edge or normal to it would be along 110 direction. And as it turns out that it is usually the direction for most of our structures anyway. So as long as all your beams are, let's say, parallel to this 110 direction or normal to it, you get the same Young's modulus of about 169 gigapascals from it. Now the other case, E11, the 111 direction, what you need to do is that I would suggest, I'm not going to solve it, I'll give you the final answer, but I suggest that you do that for your own. If you have a cube, it's a line, it's a direction that goes from one end of the cube, one corner of the cube, to the opposite corner in 3D space. So what you need to figure out now is what is the angle between that diagonal elements with each of the three axes, x, y, and z axis, right? And, well, it's obvious that the three of them are equal, so all you need is to figure out one of them, and then the other three are the same. The other two are the same. And I actually have the number for it. So I'm going to give you the answer, but the sign of that angle is square root of 2 over 3. Okay? So that's the sign of that angle, but just go and solve it for yourself. And if you go and solve or find out the, let's say, estimated or effective or equivalent Young's modulus, the number should be about 187 gigapascals. So E11 is going to be around 187 gigapascals. So it is the stiffest direction, at least among these three that we talked about. But it's not a direction that you can normally use. Let's say if you have a 100 wafer, which is your typical wafer, 111 is going into the wafer diagonally. So it's not a direction that is convenient for micro device design. In most cases, if you have normal lines and directions, it's 111, 110. And if you have something at 45 degrees relative to 110 direction, it is 100. These two are your common, the first two that we mentioned, are your common values, 130 or 170 gigapascals. And quite often you don't have, or you try to keep your design simple and don't use other directions. If you have situations where you have, for example, curved beams or spiral structures or things like that, you can come up with an approximate solution using some value in between, let's say 130 to 170 gigapascals, and leave the exact solutions, if they matter to you, to simulations. So that's that for our discussion on the material response, mechanical response of materials. In the next lecture, we go and look at the static response of some structures, most importantly, a beam, which is a fundamental mechanical component in microsystems. Thank you.